In this video, we'll look at solving trigonometric equations by using identities. We've looked at this point at a few different approaches to solving trigonometric equations, namely beginning by looking at the solutions for a trigonometric equation on a single period, and then extending that to many periods, so you have infinitely many solutions. And then we also looked at using factoring to solve trigonometric equations. Now we'll use identities, the things that we've been learning for a little bit now, where a given equation is true for any given angle theta. We'll use identities to help us solve trigonometric equations. So we'll just look at two examples in this video. First, solve sine of 2 theta minus cosine theta equals 0. So let's begin by writing this entire equation in terms of just theta. No double angles because that will complicate our solution. So let's write the first term in terms of just theta. Now we know that sine 2 theta we can easily write as 2 sine theta cosine theta, and then we have a minus cosine theta equals 0. So we use our double angle formula there. And now we'll factor out cosine theta. So we have 2 sine theta minus 1 equals 0. And then by the zero product property, we must have either cosine theta equals 0 or 2 sine theta minus 1 equals 0. So that means that sine theta equals 1/2. So the angles theta that make cosine equals 0 are pi over 2 and 3 pi over 2. And then what are the angles theta that make sine equal 1/2? I think that would be pi over 6 and 5 pi over 6. And now, of course, these solutions are just on one period of the trigonometric functions sine and cosine. So then we need to write theta equals pi over 2 plus 2k pi. Theta equals 3 pi over 2 plus 2k pi. Theta equals pi over 6 plus 2k pi. And theta equals 5 pi over 6 plus 2k pi. And this is all for k in the integers. So we use our double angle formula to help us get to one point where we have an expression in terms of just theta, no double, or sometimes you might even see a triple angle inside the trigonometric function. And then we factored and then solved for the angles that made each factor equal 0. Now let's solve cosine theta plus 1 equals sine theta on the interval 0 to 2 pi. So this one, we can be a little bit clever with our approach to this. And what I suggest we do is square both sides. So we'll square cosine theta plus 1 and sine theta. So if we FOIL cosine theta plus 1, we get cosine squared theta plus 2 cosine theta plus 1 equals sine squared theta. Now if we rewrite sine squared theta in terms of cosine squared theta, we have cosine squared theta plus 2 cosine theta plus 1, and that equals 1 minus cosine squared theta. Move everything over to one side, so we have 2 cosine squared theta plus 2 cosine theta, and then the 1's cancel, equals 0. Factor cosine theta out, and actually we can factor 2 cosine theta out, so we have cosine theta plus 1 equals 0. And now the question is, what angles theta make cosine theta equals 0, or cosine theta equal -1? So for the first factor, 2 cosine theta, the angles theta on the interval 0 to 2 pi that make 2 cosine theta equals 0 are pi over 2 and 3 pi over 2. And then the angle that makes cosine theta equal 1 is obviously pi. So we manipulated the equation by squaring both sides, then using our Pythagorean identities to write the equation in terms of a single trigonometric function. We factored and then solved for the angles in the specified interval that made each factor true. We can solve simple trigonometric equations where we might just have cosine theta equals a half. We can factor, we can use our identities, and this is a really powerful set of tools for us to have to solve trigonometric equations.